Alright guys, thanks for hanging in there with me for a second video. Be sure to leave a comment down below so that I know who's going the extra mile and getting extra support, and really pushing themselves further to gain some more exposure to this idea before class tomorrow. I'd really appreciate that. So as I mentioned at the end of the last video, I'm going to walk you through an example now with triangles. So if you read with me up here, we're told that a solid has the triangle enclosed by the line x plus y equals 1, the x-axis and the y-axis as its base. If cross-sections taken perpendicular to the x-axis are right isosceles triangles with one leg on the base of the region, determine the volume of the solid. So first things first, I did take this guy right here and solve it for y in order to use my calculator to graph that line. But once I did that, I can see really clearly the base that they're talking about right here, the triangle that I see formed right there in quadrant 1. And the big thing here then is that the cross sections that we're going to use in this case to stack along that region are not going to be squares, but instead right isosceles triangles. And this is going to be real bad. You thought my squares were bad. Check this out. I'm going to draw my rectangle, and I'm told that that guy is one leg of my right isosceles triangle. That's on the base of my region. So then I'm going to come out of the screen, that's the height of my triangle, and connect right here. And I know it's bad, but that's supposed to be the right angle right there. And this guy should actually be like three-dimensional right here. So again, forgive me. I want you to make sure that you're remembering and thinking back to those demonstrations that I showed you in class today to really try and visualize this. That's not the main goal of these videos, the drawing, but more so the computation that we're going to try here after we get our setup done. So, as in the last example, I need you to rewind back to geometry for a second. In order to be able to set up this integral, I need to first be able to remember the area of a triangle. And you guys are pretty good with this one. I hope it's not news to you that that would be 1/2 base times height. Now, the tricky thing in this example, and the really key lever for this, is that I can extend that formula not just to the area of a triangle, but how about the area of an isosceles triangle? Because that's what I've got in this case. And this particular isosceles triangle, as you can see right here, has a base that's actually equal to the height. So for me, this original formula of 1/2 base times height can actually be written as 1/2 base times base, since an isosceles triangle has two equal sides. So if you're a visual person and you're having a hard time seeing it, take a look at this triangle over here. The base and the height I've represented with B and H, but since this is isosceles, these two suckers are the same. So couldn't I label this instead of B and H? How about B and B, since these guys are equal pieces? That's all I've done here in order to help myself with my integral expression in a minute. That is absolutely 1/2 base squared. So if you can get on board with that, then the integral is going to be from some value to some value of the 1/2. Remember, I like to take constants out of my integral expression of the base of my triangle squared. So remember, if I can just figure out a way to represent that base in terms of function notation and then think critically about my bounds, I'll be able to do the calculus necessary to solve this problem. And as always, to figure out what goes inside my integral, I'm going to revert back to the rectangle that I drew at the very, very beginning of this process, which represents the base of my triangle, and address the question, what's on top and what's on bottom. So in this particular case, I've got my integral, I've got my half out front. The base here is the line, negative x plus 1, minus the x-axis, 0. squared. The bounds are a little bit tricky, I guess, if you are not familiar with linear functions. I would definitely urge you to think critically about this for a second. The starting x-bound is 0, and the final x-bound, keep in mind the curve is negative x plus 1, so this y-intercept is at 1, and my line is going down 1, forward 1, so this is also at 1. And there are the bounds on my equation. And that's about it. This, we were told, was a calculator active question, so if I wanted to clean this up, I would simply have the integral from 0 to 1 with that 1/2 out front of negative x plus 1 squared. And from here, if I can capture this, yep, I would simply go to a calculator page and put my 1/2 out front, get my integral expression, run from 0 to 1, whoops, let me put that 1 up above there, open a parentheses, and if you already had the function in f1, you definitely wouldn't have to type this. You could just type f1 of x squared. But I'm not sure if I'm linked up, so I went ahead and typed the entire thing here. And calculate my integral with an answer of 0.16667. And, whoops. There you have it. Another volume of a known cross-section. So again, just to sum that up, you're really making sure that we have a foundation of our geometric area formulas that are going to lay the groundwork for our integral setup. Again, last time, remember, for a square, I just had a side squared. There was no constant out front because it didn't make sense to have a constant out front since the area of a square formula has no extra constant. With a triangle, though, like in this example, I hope it's really feeling logical that there's a 1/2 out front since the area formula for a triangle has a half in it. So we will talk in more detail about what happens with some more interesting things like semicircles and some special rectangles that we'll get exposure to, especially an equilateral triangle as well. But for right now, I think you've got a really solid idea of what's to come. And so with that, enjoy the rest of your night, and I will see you tomorrow.